Hello everybody, and welcome to the National Weather Service in Burlington's presentation on downslope windstorms in the Green Mountains, causes and correlations with easterly wind anomalies. My name is John Goff, and I'm a lead forecaster here at the National Weather Service in Burlington, Vermont. And this recording was originally recorded back in early March of 2016 and is re-recorded here for your benefit. It'll approximately last about a half an hour or so. So with that, let's go ahead and get started. Here are the discussion topics for today's presentation. First, we'll talk a little bit about windstorm climatology in the Green Mountain State. Then move on to factors affecting flows in complex terrain, how wind flows around mountains more or less. We'll then talk about pressure gradients and gap wind flow. And finally, we'll wrap up the discussion on some talk about numerical weather prediction and easterly wind anomalies. Okay, let's talk about a little windstorm climatology about our area and in the world in general. One thing is certain, downslope windstorms are a common climatological feature in many mountainous regions of the world. They're known by many names. They can be known as foehn winds or katabatic winds. Shropshire winds are a local downslope wind that occurred in the southern Green Mountains back in historical time, and some of you may be familiar with that name. Chinook winds and Santa Ana winds are also other downslope winds. They can produce extreme wind gusts, in some cases more than 100 miles an hour. And in the map I show here, there are some generalized areas around the world that these occur. South of the Himalayan mountains in Asia, south and east of and west of the Alps in Europe, Greenland, the western parts of North America and South America, and also off the Antarctic ice shelf is another place where downslope windstorms can occur. There are many regional effects and localized effects with these storms as well, and I've shown a couple more regionalized maps of Europe and the western continental United States. So you can see here in Europe there are many forms of these winds: the Kosovo wind, Bora wind, Mistral wind coming off the Alps. You may have heard of some of these. In the western United States there are many forms of these winds: Wasatch winds, Chinook winds, we spoke of those, and the Santa Ana winds in Southern California. In terms of Vermont in particular, we have a history of damaging wind events in the state. Here are a few listed in the more contemporary times, the most recent really major one being on December 1st, 2010. We also had a major windstorm in Rutland in April of 2007, January of 1996, and back onward through time. In terms of that 2007 event, particularly on April the 16th in Rutland, Vermont, we called that the Noricane. That was a common coin term that was given to this windstorm. 60 to 80 mile per hour wind gusts were observed in the city and close by. Approximately $5 million in damage, mainly due to trees and power lines. And there were about 60,000 power outages. Luckily, this did occur in April, so we weren't dealing with widespread Arctic chill. It was milder. However, there was widespread damage in the city and up and down the western slopes of the Green Mountains in southern Addison County and into Rutland County. A major storm. In terms of downslope wind climatology in Vermont, it generally favors the western slopes of the Green Mountains to approximately 10 miles west during strong easterly wind events. I've attempted to highlight some of the more favored areas shown here on the map at right. These are just generalized areas. These by no means are exact. Localized winds across the state can be higher or lower depending on where you are. I've attempted to highlight the main areas where you would see the easterly downslope winds, and most particularly make note of along the western slopes of the Green Mountain spine, a very common place to see these storms. Secondary maxima wind are also scattered across the central and northeastern part of the state. Okay, let's move on and discuss factors affecting flows in complex terrain, mainly winds and how they behave and interact around mountain barriers and higher level terrain. There's two or three main points I'd like to bring up here. One is about atmospheric stability. We'll talk about airflow, both speed and direction, and then we'll also talk about the topographic characteristics of the mountain barrier itself. So first, let's talk about atmospheric stability. When we talk about stability in the atmosphere, we always use terms stable versus unstable. Stability is basically equivalent to buoyancy, or the level of buoyancy in the atmosphere. When you have a stable parcel or a stable environment, such as the top panel on the image at right, The parcel tends to sink if lifted. It's resistant to upward motion. This is a case where you have warm air atop cold air. Cold air is generally heavier than warm air and will tend to sink. So if you have a situation where there's warm air aloft, that cold air will stay in place. It's a very stable environment and does not want to mix, and it likes to stay that way. The boundary separating the cold from warm air during a stable type of environment is called an inversion. Okay, an inversion just means reverse, because normally you have cold air atop warm air and the atmosphere is slightly unstable a lot of the time, and the parcel will continue to rise if lifted. It's buoyant. So an important consideration, stability of the atmosphere. Is the atmosphere buoyant, meaning unstable, or is it a stable environment where it wants to stay in place? Here's the stability cross-section. Stable conditions on the windward side of the mountain barrier, in this case on the left, are favorable, and we also talk about things like blocked flow. So a common case scenario is where you have cool, stable air to the east of the mountain, or on the windward side of the mountain. It's cool and stable, and it's blocked from flowing over the mountain. If it can flow over the mountain, then it will descend and warm and rapidly dry. Typically during downslope windstorm events, we want to look at this type of setup, where you have stable, cold air east of the Green Mountains and more warm, unstable air west of the Greens. Though this could be reversed in any case north, south, east, or west, depending on the mountain barrier and the area of the world you're in. When we talk about the roles of inversions, basically it's an increase in temperature with height. We saw that on the previous graphic a couple of slides ago. The inversions generally impede the propagation of energy, right? It's a stable atmosphere, so the cold air wants to sit there and not move. Buoyancy-driven oscillation occurs in stable layers, not in unstable layers. And so what happens, as you can see in the temperature, or the diagram here shown, the air is moving from left to right. It's moving quite quickly. Then it runs into this stable layer east of the Green Mountains. It slows down. The mountain barrier is blocking that air from moving. But the air that does get over is pinched and squeezed and then rushes down into the unstable air on the other side of the mountain. So the roles of inversions can be very key, and really a lot of times when we look at downslope windstorms, if the inversion height is right about the top of the mountain level, that can be quite critical because it can block the air from generally flowing over the mountain at all, and then when it finally gets enough energy to be pushed over, it'll rush over and spill down onto the western side of the mountain, sometimes in very strong fashion. One of the factors that we look at when we talk about stability is something called the Froude number. I won't get too much into this. It's basically an energy, a unitless energy index. The kinetic energy is divided by the potential energy of the system. So you basically take the wind speed and divide it by the factor of stability of the atmosphere times the height of the mountain barrier. If the Froude number is about equal to 1, mountain waves are likely. If the Froude number is much less than 1, the flow is blocked, meaning maybe that cold layer is really dense and stable on the east of the Green Mountains. The inversion is below the mountain top level. The flow is blocked from getting over. Or if the Froude number is much, much greater than 1, the flow will go right over the mountain with no oscillations. And this would be a case where the atmosphere is generally unstable and you're well mixed, well higher than the mountain barrier itself. The Froude number we use quite often, especially in the winter time, to look at certain types of weather setups, whether that's from upslope orographic precipitation or in forecasting downslope windstorms. So again, here's just a little more detail in the Froude number. If the Froude is approximately equal to 1, orographic waves and breaking waves are likely. Downslope windstorms are a possibility if the wind flow is strong enough. When those Froude numbers are right equal to 1, imagine that inversion height right at the top of the mountains. If the Froude number is less than 1, the flow is blocked. This would be favorable for gap windstorms, and we'll get a little bit more into that later in the presentation. This is where the wind would just flow through the gaps in the mountain barrier, like a mountain pass or a river valley, but in general would not be able to flow over the broad spine of the Green Mountains. And finally, if the Froude number is greater than 1, the flow is unblocked, the free flow is over the mountains, and in general the high wind threat is lower. Okay, moving on to the second criteria, airflow, when we talk about wind interaction with mountains. One of the common features in wind in the atmosphere is something called wind shear. It's always present. It can be weak to strong depending on the day in question. Wind speed shear is often present from the surface to the mid-levels. In this case, we're just having an idealized example in the graphic here. The winds aloft are generally blowing considerably stronger than winds at the surface, so you have a wind speed increase with height. On any typical day, you always have some level of wind shear. Generally, it's not that strong. During downslope windstorms or under a strong winter storm or other type of environment, a severe weather outbreak, for example, the wind shear can be quite strong so that the winds aloft are blowing much, much stronger than the winds at the surface. When we look at the lower levels, these real strong differences in winds can be called shear zones, and this is one thing that can be very important in aviation, which is a different topic altogether. But high wind shear and shear zones can be a hazard to aviation. So here's a graphic that's basically a two-dimensional graphic that shows how low these wind shear zones can get. Again, we're looking basically from the surface to about 13,000 feet in this diagram, denoted by the white numbers, the thicker white numbers, 1K, 2K, 3K on the right side of the diagram, indicating 1, 2, and 3,000 feet. And then the wind speed is outlined by the colored shaded lines in the graphic. And here you can see between Wednesday at 7 a.m. and Wednesday at 7 p.m. on this date in question, the winds aloft are blowing much, much stronger. You can see how you have 80 to 90 knots of wind all the way down to about 3,000 feet, and about 60 to 65 knots of wind, which is roughly about 75 miles an hour, all the way down to about 1,000 feet, quite low. So if those winds are blowing like that and you have a mechanism to get them to the surface, you could be dealing with some pretty hazardous conditions. Favored directions for downslope windstorms, at least in the Green Mountains, is from the east to southeast. But in terms of any given mountain barrier, you want flow orthogonal or perpendicular to the mountain barrier. That's the most optimal. You want it hitting the mountain barrier head on. Windstorms can still occur if it's not perpendicular, but it's of generally a lesser magnitude. So I've attempted to show the previous climatology plot I showed you earlier, and then draw on the wind barbs there that are favored directions. So you can see generally east or east-southeast are your favorite directions in the Green Mountains to get these storms. Of course, most of the time the winds are blowing from the west, but generally speaking, when you have strong westerly winds, they're not of the typical setup that you would get the downslope windstorms from the east. You don't have cold air to the west and warm air to the east, and the stability-instability setup is not the same. Finally, when we talk about airflow interactions with mountains, we want to talk about the mountain barrier characteristics itself, the characteristics of the topography. A lot of times when you get these big breaking waves that come over the mountains, they kind of fan out into like waves downstream of the mountains. The amplitude of these big orographic wind waves are dependent on the structure of the atmosphere. We talked about that earlier. Stability in there, stability unstable, the nature of the airflow, or orthogonal to the barrier, but also the size and shape of the mountain. Typically, the sharper the barrier, the greater the amplitude. So the higher the mountain peak and the sharper it rises and falls, the greater the amplitude. A low sloping mountain would not give you as much of an effect as a barrier. Another thing is a dome of mountains. A dome of mountains, typically, you also don't tend to get quite the magnitude of windstorms as a barrier of mountains. That's why often when we get a lot of these storms, you don't see the real strong winds in the Adirondack regions as much as you do on the Green Mountain side on these easterly flow events, because the Adirondack Mountains are typically a dome and the winds will tend to generally flow around that dome. Think of the Adirondacks as a pebble in a stream and the wind flow just flows around it. Now certainly you can get strong winds in the Adirondacks, I'm not suggesting that, but in general the downslope windstorms from the east typically affect the Green Mountains greater than they do the Adirondacks. Another point to consider is focused flow. When you have these easterly winds, waves can be of higher amplitude or focused where the barrier is convex to the flow. So when we look here in the Rutland area or the southern greens, you notice in my red shaded area how the Green Mountains kind of bow out to the east there. Well, if you get a due easterly wind there, it's basically convex to the flow, and then the flow is focused inward to the west side of the greens. And sometimes when you get focused convergence of the flow like that, you can get an increased magnitude in the winds as well. So focus flow, another thing to consider when you're forecasting these events. Downslope winds from mountain waves. One thing to consider when you're talking about stable and unstable, very cold stable air, warmer unstable air, they typically, in terms of the climatology, happen more in the cold season, winter into early spring. And the wind gusts are often double the sustained winds. They can be warm or cold winds. Generally, all downslope winds are warm, but if the air mass replacing if the air mass that's rushing down the mountain is so cold that it displaces the warmer air on the western side of the mountain, or whatever side of the mountain it's coming down, it can actually be colder. Downsloping winds generally are warming as they downslope because they're being compressed. But if it's so cold to start with, it can actually be colder when it arrives. Typically, downslope winds are warmer winds, though. If you look on this plot from Austria and the Alps, you can see how the wind gust in that teal color around about the middle of the chart there can be as much as almost double the sustained winds, which is in the pink. So it can be quite a bit of a magnitude difference. When we talk about visual characteristics, a lot of times these things are happening within cloudy skies or clear skies sometimes. Sometimes if you get the mountain waves and there's enough relative humidity in the lower atmosphere, you can get lenticular clouds form atop and downstream of the mountain barrier on the crest of the lee waves. This occurs when the wind speed increases and the stability goes down. Okay? This is taken from Essex, Vermont, looking west across Lake Champlain from Burlington, Vermont, and you can see these lenticular clouds, these darker clouds. They look very striated. Sometimes they appear almost like a flying saucer, indicative of strong wave action and trapped lee waves with strong winds blowing across the mountains. Now, on this day in question, we really didn't have downslope windstorms. This just illustrates these wave-type characteristics that will set up as air flows over the top of a mountain barrier. When you have the other characteristics start to set up, then these waves can make it all the way to the surface and you get the windstorms. But sometimes you'll see these lenticular flying saucer looking clouds, and that's indicative of stronger winds blowing across the mountain crests. Okay, moving on to the next topic, let's talk about pressure gradients and gap winds. When we look at gap winds, we're really talking about winds being forced through small, narrow constrictions in the mountain barrier. So earlier I talked about things such as river valleys, where the Winooski River or the Winooski River or the Lamoille River, some of these rivers go through gaps in the mountains, or in restrictions like Brandon Gap or Lincoln Gap, where you have a low spot in the mountains. The strongest winds in these typically occur in the restrictions, the narrowest part of the gap, and generally occur in the gap exit region. So you can see in the diagram here, the flow is coming from right to left. Imagine this is the Green Mountains. The wind gets slowed down and squeezed through the mountain gap, and then as it exits, it really increases in speed. It's basically a conservation of energy and motion in this type of case. And so to maintain that, it accelerates out of the gap. The Venturi effect or the funnel effect, these type of effects dominate on the small scale. So when you see these type of flows exist, this is when you have very, very blocked flow, very stable. The air cannot get over the mountain barrier, but it's forced through these low spots in the mountains, gaps. That would be when a Froude number is much, much less than 1. And the role of pressure gradients is vital in this process. Pressure and the airflow generally flows from high to low pressure. It's a known fact. And the pressure gradient will blow from these high to low pressures. So the strongest flow goes from the high over to the low through the gap area. And again, the gap flows are most prevalent, as I mentioned earlier, when the Froude number is much less than 1. And the picture shows this. This is a radar picture from our Colchester radar in Chittenden County, shown by the black hole dot there just north of BTV, which is Burlington, Vermont in Chittenden County. And what you're looking at here is a velocity profile from the radar. The radar can not only see raindrops, but it can see wind and wind flow and can detect the direction from where that wind is flowing. Greens in this case are blowing toward the radar. Reds are blowing away from the radar. So if you look at this case, you can see the winds are blowing toward the radar from the south and the east and are blowing away from the radar to the north and the west. This is indicative of winds blowing from the southeast. And the thing I want you to take particular note in is look along the Green Mountains between the Washington-Chittenden County line and down into eastern Addison County. And can you see those kind of striated features in the velocity profile? Looks like little stripes that kind of oscillate back and forth. Those are gap winds occurring during strong gap flow during a southeasterly wind event. There's some surface wind observations overlaid in here, and you can see a few of the wind gusts, of those of you familiar with reading METAR observations, of 30 to 40 knots or 35 to 45 miles an hour in some of these gap wind locations. So these are another tool we use, at least locally in the Weather Service, is to look at the radar velocity profiles to detect some of these stronger gap winds. Of course, you have to use a variety of tools, model data, as well as surface observations. Okay, our final topic we talk about is numerical weather prediction, basically weather models, and easterly wind anomalies, and their importance in forecasting these types of events. NWP, numerical weather prediction, can be vitally important. They can be valuable information and can provide conditions that lead to mountain wave activity and downslope winds. The required horizontal resolution really needs to be quite fine when you're talking about gap winds, a river valley or a gap. These are small scale features, so you need to have a model resolution that's small enough to pick these up and show these. So 10 kilometers or less is good to provide, is probably needed to provide good details, and even smaller resolution is probably ideal, 4 kilometers or even 2 or 1 kilometer, to really show the detail that you want. They do tend to have difficulty generating accurate wind forecast in terms of speed, but can definitely forecast the high winds at the mountaintop level and show geographically where the strongest winds will occur. This is an example of our 4-kilometer locally run model, Weather and Research Forecast Model, WRF. We run here locally, and this was run during the Downslope Windstorm in Rutland back in April of 2007. The shadings on here are wind speeds. We call these isotachs. That's the name for it. You can look it up on Google if you want. It's basically just shaded wind magnitude. And what I just wanted to show you, this is a very strong southeasterly wind event. Notice how the strong winds are affecting the southeastern areas of the Green Mountains, particularly to the west of the Greens, from central and southern Addison County down through Rutland and Bennington County, and also to the leeward side of the White Mountains in New Hampshire, and other little areas across the central and northern part of the Green Mountain State. And if you look at some of these magnitudes, it's showing 40 to 50 knots, which is 45 to 55 miles an hour. As we knew, the winds in Rutland were much stronger than that. Again, alluding to the fact that this really didn't depict the magnitude of the winds that were observed, but was valuable in showing where they were likely to occur. So again, numerical weather prediction, a big help in a lot of these events. And we have a lot of procedures in the Weather Service office here in Burlington, as well as many other offices around the nation that can help with these types of setups. One of the things when looking at numerical weather prediction and weather models is assessing the value of easterly wind anomalies. What I mean by anomaly is how anomalous is it? How unusual is it? Okay? Westerly flow is by far the most dominant wind regime. Most of the winds are going to come from the southwest, the west, or the northwest. Occasionally they'll come from the east and southeast, and when they do, how anomalous is it? So when you compare the flow to normal conditions, it can be very helpful in assessing potential strength of a system. Again, easterly flow is uncommon in general, and anomalies are expressed in the standard deviation from normal conditions. Standard deviation is just a term of how anomalous something is, of 1 standard deviation away, 2 standard deviations away. So the greater the anomaly, the greater the standard deviation, the greater potential impacts could be. Wind anomalies are available on a variety of websites. These are internally generated by a website at Penn State University. And this is showing the windstorm in Rutland. One of the things I wanted to show you is basically the right-hand panel there. The gray shading and purple shadings, those are 4 to 5 standard deviations above normal of easterly wind anomalies. They have negative values because easterly winds are negative in general because they're uncommon. We determine positive flow is from the west, negative flow is from the east. So look how negative it is in Vermont at about 12Z, which is about 8 a.m. on April 16th of that year. And if you remember, it happened during the early to mid-morning hours if you lived in the Rutland area. 4 to 5 standard deviations above normal easterly flow. Very anomalous, very unusual, gives the forecaster a better sense of how unusual or strong the winds may be. Okay, as we wrap it up here, let me just go through a quick summary. Downslope windstorms occur in many mountainous areas of the world. We showed the world map and some regional maps for you. In our area, they typically affect the western slopes of the Green Mountains during strong easterly flow events. And the primary factors affecting downslope winds are atmospheric stability, airflow speed and direction, and the topographical characteristics of the mountain barrier itself. Pressure gradients dictate directional flow from high to low pressure. And gap winds are a small-scale phenomenon where funneling or Venturi effects will dominate. Remember, that's when the flow is completely blocked, Froude number is less than 1, it can only get through the gaps. Numerical weather prediction is a valuable tool in assessing the strength of easterly wind anomalies. And high-resolution models, such as the 4-kilometer WRF we run here locally, or even a higher resolution model, they're necessary to capture the real small-scale details that are common in many downslope windstorms. There are a number of references I used in the presentation that you viewed here. Comet Meteorologist, that is a free website that you can go to if you Google Comet Meteorologist weather, and they have a whole wealth of information about weather forecasting, marine wave forecasting, and it's free. You just have to sign up with a login ID, and you can take all the training you want if you're really interested in weather. And some of the presentations that they have, including mountain waves and downslope winds, gap winds, mountain waves, and a case on the Yukon downslope windstorm, were taken for this presentation. So that's the website there. And the social network at NOAA.gov website, that is a website that we run here locally. If you view this presentation and have a question that you'd like answered, shoot me an email, John Goff, at that email there, and I'll be happy to get back with you and try to answer your question if you have one. Again, thank you for your time, and I hope you gained a little information about downslope windstorms in the Green Mountains. Have a nice evening.